Good morning, guys. Good to see you all. Today we have Lisa, who's going to talk about cubic hypersurfaces.
Yes, thank you very much for asking me to give the talk. So today I'm going to talk about cubic hypersurfaces. This is kind of going to be, I'm not going to prove very much today. That's kind of my goal, is just to give you kind of an overview as to why people care about cubics, why I care about cubics. And feel free to interrupt with questions or whatever as we go. So first, I want to start with just reminding everybody kind of the setup. So this is a topic in projective geometry. So I'm first going to just remind you of projective space. So whenever I write this kind of bold Pn, this is always complex projective n space. So if you remember, this is just n plus 1 tuples, so x0, x1, up to xn. So this is in Cn plus 1 without the origin. And then we just add this additional relation. So we say x0 up to xn. This is the same or equivalent to lambda x0, lambda x1, all the way up to lambda xn, where lambda is in C star. Okay. So this should be familiar. Of course, this is a complex manifold. Okay, so today we're going to be dealing with hypersurfaces of projective space. So all we need to know is what is a hypersurface. So a hypersurface, let's say X, inside of projective space, well, it's just going to be given as the vanishing locus of a single polynomial. So f is just a polynomial in variables x0 up to xn. We're just setting this to be 0. And this f here is going to be a degree d, let's say a homogeneous polynomial. So here we also say that the degree of x, this is just the degree of the polynomial that defines x. All right. Okay, so the main object of this talk is going to be degree 3 polynomials. So when I say a cubic, like a cubic n-fold, this really just means a degree 3 hypersurface that is n-dimensional. So n-dimensional. So that just means it's sitting inside projective space of 1 dimension higher. Okay. So these are kind of like the main players. But before we kind of get into this, let's just start kind of in low dimension. So I want to just start in the projective plane and talk about curves for a little bit. So
Lisa?
Yeah.
Sorry to interrupt.
Okay.
So when if you scroll up to the definition of, you said a hypersurface.
Yep.
To me, and I'm sure this is wrong, but because I'm not an algebraic geometer, but to me, it looks so much like the definition of what I think of as an algebraic variety. And so I'm wondering if you can say what the differences between those are.
Yeah, so it's an example of a variety. Yeah. The key point here is it's given by a single equation. So algebraic variety can be given by a bunch of equations, by the vanishing set of a bunch. And so a hypersurface is just the special case when it's given by a single polynomial.
Okay, thank you.
Yeah. All right, good. Okay, so let's start by discussing curves. Okay, so if we're interested in curves, or in particular plane curves, what I really mean is hypersurfaces of the projective plane, so P2. So a curve is just, or a plane curve, sorry, is just going to be a hypersurface of P2. So here P2 has x0, x1, x2 coordinates. Okay, so we're interested in cubics, but before we get to cubics, I just want to mention a couple of, let's see why we don't really care about linear things and degree 2 things. So why do we start at degree 3? Okay, so the first thing is if we have a line in the projective plane, well, I mean, we can just write this down in equations. It's going to be given by an equation that looks like something like this. And we can very kind of easily see, so if we take the 0 set, let's call this L, this is my line. I can easily see that L is going to be actually isomorphic to just P1. And I want to kind of just stress how we see this. So one way to see this is to exhibit a morphism between my line and the projective line, P1. So what is my line? So my line has coordinates x0, x1, x2 that satisfy my equation up here. And it's kind of easy to get a map to P1. I could just forget one of the coordinates. So I could just forget the last coordinate. And that would be fine. So this is kind of what's called a projection map. And what we want to do is also do an inverse. So a map from, I'm going to write it like this. So from P1 to L. Well, my P1, let's say, has coordinates Z0, Z1, just to distinguish. And I really want to try and get, when I map it to L, I need to give kind of 3 coordinates which satisfy this equation. So one thing I can do is I can just send it to Z0, Z1, and then Z2 should just, like the last coordinate, should basically just be, we can just solve this equation for the last coordinate. So you see that this would be like minus A0, Z0, minus A1, X1, divided by A2. Sorry, I kind of ran out of space. And you can check that these are inverse to each other.
I guess we are assuming without loss of generality that A2 is non-zero, is it?
Right, yeah, so in our equation, we have these 3 coefficients, A0, A1, A2, and we know that one of them has to be non-zero. Yeah, so we're assuming A2 is non-zero. Good point. All right, so this kind of seems a little bit obvious, but the reason I want to kind of do this is because it's going to set us up nicely for the idea of rationality. So what have we done here? So my map from P1 to L is an example of what's called a rational parameterization of the line L. Okay, so what have we done? What do I mean by this? I mean, I can write the coordinates for my line in terms of some rational functions. So in here, these are actually linear, right? We have just Z0, Z1, and then we have some linear combination. Sorry, this should have been Z1. We have some linear combination of Z0 and Z1. So we can ask the question, for a general plane curve, inside P2, when does it have a rational parameterization? Okay. Okay, so the next example is kind of conic. So what is a conic? So a conic is just going to be a curve inside of P2, which has degree 2. All right, so if we look at the equation of C, the monomials are all just degree 2. Okay. So for this, I'm just going to consider an example. So let's consider the curve x0 squared plus x1 squared minus x2 squared equals 0. So this defines a curve inside of P2. And again, we want to see if we can write this, if we can somehow relate this back to P1. So this should kind of be something familiar in a second. So let's look at a picture of this in a standard chart. So I want to consider the chart where x2 is non-zero. So remember P2, this is x0, x1, x2, and not all three coordinates can be 0 or 1. So let's just look in the chart where x2 is non-zero. In this case, I can divide everything. So my equation is going to become x0 over x2 squared plus x1 over x2 squared minus 1, but I'm just going to move that to the other side. So it's going to be equals 1. And so we just have the equation of a circle in this affine chart. So let's just consider the picture. So if we take the unit circle, oops, straight line. What we can do is we can construct a map from C to the projective line in the following way. So in this chart, what we can do is we can look at the North Pole. So again, this is what this is 0, 1. And we can just consider stereographic projection. So we can just take the lines, or maybe that was a bad example. We can take lines through this North Pole. They're going to hit my circle in exactly 1 point. And I'm going to map this point down to this point, which is, I guess in this picture, this is just C. Okay. And if you write this kind of down in coordinates, this is going to be the same as taking these coordinates and mapping it to x0, x1 minus x2. This might not be exactly right, but you can kind of see what I'm doing. Okay. And so this morphism from C to, well, this map from C to P1, just by projecting through these lines, is going to be defined everywhere on the circle apart from the North Pole. So in order for this to be a well-defined map, we can just look in a different chart. So we pick the chart x2 is not equal to 0. And so what we could do is we can do the same thing. In the chart, say x0 not equal to 0. And we can glue these maps together. So it's an easy exercise, I guess. So easy exercise. To check that you can glue these maps to get an isomorphism from this conic that was sat inside of P2 with P1. Okay. Are there any questions so far? Everybody good?
I have a question.
Sure.
So it seems like, I mean, all the pictures we're doing are in like the real setting.
Yeah.
And so
Yeah.
I'm wondering if it's obvious that sort of the techniques or the ideas translate easily to the complex setting, or I mean, how this is different in any way.
Yeah, I mean, so it's not going to be, yeah, that's a good question. These kind of pictures are definitely the real picture. But when you write everything down in coordinates, it kind of, it goes through. So kind of at the level of small dimensional things, kind of the real picture is enough to give you the correct geometric intuition. It gets a little bit trickier in higher dimensions. So these pictures kind of don't really work as well as you might hope. But this works exactly the same. And like, I mean, if you've done like complex analysis, this is exactly the stereographic projection to prove that, you know, we do it in like with P1 being a sphere and stuff.
Right.
That kind of stuff. This is exactly the same idea.
Okay.
Yeah.
Thanks.
All right, so in fact, so I did this for a special, we just looked at a special example, but in fact, every degree 2, so this is what's normally called a conic, so curve in P2 is isomorphic with P1. So kind of from this point of view, degree 2 and degree 1 curves in P2 are not super interesting. They're just isomorphic to the projective line. We know pretty much everything there is to know about the projective line, and so they're kind of not really worth looking at. But degree 3 is where things start to get non-trivial, even in the curve case. Okay. So we're going to next talk a little bit about cubic curves. How am I doing for time? Ah, good. Okay, so cubic curves. So again, a cubic, maybe I'll just write a subscript 3 for now. So this is just given by a degree 3 polynomial in 3 variables. And so I'm actually just going to change my my coordinates to just x, y, and z instead of x0, x1, x2. Okay, so if you write down a degree 3 polynomial, you have, you know, lots of monomials, and you have a coefficient, complex coefficient in front of each one. But the good thing about projective space is we can always do linear changes of coordinates. And so it's possible that using just coordinate changes, so linear coordinate changes, for P2, we can always write the equation of a cubic in kind of a standard form. So we can write the equation of C as the following. So we get y squared z equals x multiplied by x minus z, x minus lambda z, where lambda here is a complex number. I'm not going to prove this. It's kind of believable. You're just doing linear coordinate changes. Okay, so here I should kind of mention, I only really care about smooth things. So I'm only interested in smooth hypersurfaces. So this is kind of just an aside. What does this mean? So if I have an equation, my hypersurface is given by an equation equaling 0. I just want, there does not exist any points. So say this was x. There's no points on x where all the partial derivatives of f simultaneously vanish. Okay, so if I have this equation for my cubic, let me just write it down here again. I want my cubic to be smooth. And in that case, you can see that lambda can't be equal to, so it can be any complex number apart from 0, 1. Yeah, 0 or 1. Yeah. Okay. Okay, so in the previous two examples, I kind of said how we could go from our curve and get this isomorphism to P1. So what we really care about is, can we do the same for this cubic curve? This is the next curve in the list. And so before I talk about that, let's just kind of make this a little bit more rigorous. So I'm going to give us a couple of definitions here. Okay, so what are we going to say? So an n-dimensional hypersurface. So x inside of Pn plus 1. Let's also say smooth. Is called rational if it is birational, and I'll explain what that means in a second, to projective space of the same dimension. Okay, so what does birational mean? I think, yeah, okay, so one way is to say that there exists a map from X to Pn that is given by rational functions. So functions, I mean, rational functions, just, you know, maybe not f, let's use like p of x over q of x. Okay. And what else do we need? So we also need, and there exists an inverse. So you need a rational map from X to projective space, and you need a rational map back from projective space to X. So this one is also given by rational functions. Okay. So one thing kind of to notice, also note, this is equivalent to saying that there is an open set U of X. So this is a Zariski open set. And an open set of Pn, again, a Zariski open set. Such that U is isomorphic to V. So if you don't remember what Zariski open sets is, that's kind of okay, but the key thing to say here is that Zariski open sets are dense. Okay, so essentially what we're saying, if X is rational, then X is isomorphic to Pn on a open dense subset, essentially. So there's a large open dense subset of X that's isomorphic to a large open dense subset of projective space.
Is this what it means by the dashed lines?
Pardon?
Is this what it means by the dashed lines?
Yeah, so the dashed line means that this map is not defined everywhere. So it's not going to be defined on exactly the complement of these open sets. So remember, I like to give a map to Pn. All we need to do is kind of give rational maps. Let's say like this is like F0 of a point on X, F1, up to Fn. But each of these functions are just rational functions. So whenever the denominator is 0 is exactly where this map is undefined. Yeah. And again, if you remember, the Zariski closed set is given by 0 sets of polynomials. So it's going to be undefined on such a set. Yeah. Are there any other questions? All right, good. Okay, so here's another fact. So for curves, actually birational maps are much easier. So for curves, a birational map is just an isomorphism. So if I have a birational map between curves, the only place it can be undefined is essentially just a bunch of points. And the fact is, because of the dimensions, we can always extend a map across points. Okay, I think this is some extension result in probably complex analysis. So for curves, birational morphisms are pretty easy. They're just isomorphisms. Okay, so now we come to, I guess, the first theorem. So if I have C, my cubic curve, so my cubic curve, and the theorem is that it's not rational. So the cubic curve is not isomorphic to P1. Okay, so I am going to prove this because this was kind of a neat proof that I found, which I hadn't seen before. So my curve, I said before, is given by the following equation.
Sorry, Lisa.
Yeah, sure.
You mean that no curve is rational, or a specific one that you're going to choose?
I mean any cubic curve, so any smooth cubic curve in P2. So anything given by a degree 3 polynomial.
Okay, it's never rational.
Right. If it's smooth. Yeah.
Okay.
Actually, as soon as it has a singular point, as soon as it has the mildest singularity, which is a node, it becomes rational. Yeah, so it's only true for smooth.
Okay. Thank you.
But while we're sort of stopped for a second,
Sure.
Can curve meant just like a hypersurface of P2?
Yeah, sorry, yeah.
Okay, I was not remembering, but okay, thank you.
Yeah. Yeah, this is good to remind me on these things. Sometimes, lingo just slips in without realizing. Okay. Good, so we've already said that, or you can believe me that every cubic curve, every smooth cubic curve looks like the following equation. So I want to consider, oops, I want to be in purple for my proofs. So consider the following map. So I'm going to call it I from P2 to P2. And I'm just going to send my coordinates x, y, z to x minus y, z. Okay. So this is a perfectly good morphism, and actually has finite order. So if we do I composed with I, this is obviously just the identity map on P2. Okay. So this is called an involution. So it's a degree 2 self map. Okay. But one thing we can kind of see, because this map, I mean, it's only affecting my y coordinate, I can look at its restriction to my cubic curve. So I can look at I restricted to C. And from the equation, because my y only appears with a square, it's going to preserve my equation. So this involution is going to descend to a map from C to itself. So I get an involution, an induced involution. So it induces this map of order 2. Okay. Okay, so let's look at the fixed points. This map does have fixed points. Okay, so a point is going to be fixed well, it actually has 4, and we can write them down. So if x, y, z, well, if x and y are 0, 0, then that satisfies this equation. Z can be anything, so we'll just put it as 1. So that's one fixed point. Another is 1, 0, 1, 1, 0, lambda, and 0, 1, 0. And so you can kind of check if you plug in all of these points into my equation, they do belong on the curve, so that's good. And they are fixed by the involution. And you can see that they're fixed right here by looking at the y. Okay. So that's kind of cool. So I have this involution of C, which fixes 4 points. So now we suppose that C is rational. So if C was rational, that means it would be isomorphic to P1. But what does that mean? It means we've just written down an involution of P1 with 4 fixed points. But this is already a contradiction, because what are involutions of P1? Well, we know that the automorphisms of P1 they're just the Mobius transformation. And in particular, they can't have 4 fixed points. So they can't have 4 fixed points. So we get a contradiction. All right.
Lisa?
Yep.
Would 1, 0, 0 be a fixed point? I mean, it seems to me like it would be on the curve.
I guess, yeah. Wait, hang on.
It's not on the curve.
Yeah, I don't think it's on the curve.
The left side is 0, and the right side is 0.
The right side should also be 0.
Oh,
I think you meant to
sorry.
put x minus z.
Oh, so it should be x minus z.
Yeah, I wrote down the equation wrong. Sorry.
Okay.
Yeah.
Okay.
Yeah. Good catch. Nice. So this is kind of neat. I hadn't seen this proof before. until I was preparing for this talk, so I quite like it. I don't know, I like automorphisms. Okay. So we see our first kind of example of something that's not rational. Okay, so let's move on. So this was curves. I've talked a lot about curves, but I actually don't really like curves very much. So let's move on to dimension 2. So let's talk about cubic surfaces. So a cubic surface, we're going to call it S now for surface, is just, again, a hypersurface of P3 given by a cubic equation. And actually, Dan's talk from a while ago, if people were there, if people remember, he talked about these objects quite a lot. And one thing that he said, so Dan told us that every smooth cubic surface contains 27 lines. So here, when I say line, I really just mean a one-dimensional subspace, linear subspace of the P3. Okay. So I'm not going to reprove this, but this is something that Dan told us about. And another fun thing is that there's a fact that actually you can find two disjoint lines. Okay, so you can always find two lines contained in my cubic surface which do not intersect each other. Okay, so in dimension 1, we saw that the cubic curves are not rational. Smooth cubic curves are never rational. And so in kind of dimension 2, it's kind of strange. We're going to get the opposite. Every smooth cubic surface is rational. So how do we see that? So I guess a theorem is every smooth cubic S inside of P3 is rational. And so the way that we're going to do this is we can construct a map from S to the product of these two disjoint lines. So we have two disjoint lines. Let's call them L1, L2. And so this product, each line is just a one-dimensional subspace, so it's isomorphic to P1. And so that this is isomorphic to P1 cross P1. So this doesn't, if we construct such a map and then also construct an inverse, we won't quite have shown that it's rational, but we'll have shown that it's birational to P1 cross P1. And maybe because I'm running low on time, you can believe me that P1 cross P1 is also birational to P2. So maybe let me just write that here. P1 cross P1 is rational. So there is a map from P1 cross P1 to P2 with a rational inverse. And so we'll get a rational map from S to P2 just by composing the two maps together. Okay, so how do we construct this map? So first, actually, I'm going to construct the other way. So the other way is kind of easier. And actually, I think it's defined everywhere. So let me draw a picture. This is maybe the only picture I will draw. Yeah, I can't really draw many pictures. So S, this is my cubic surface, and let's say this is my L1, this is my L2, and they don't meet. Okay, so I'm going to pick a point here and a point here. So this is P, this is Q. So P, Q. And I want to send this to somewhere on S. So one thing that I can do is I have 2 points. 2 points always define a line. So I can just draw, I can take this line. Well, it's a bit squiggly, but this line that runs through these 2 points. Another point here is that S is a cubic polynomial. And so if we want to look at the points, so maybe let's call this line, this is like the line between P and Q. If we look at the intersection of this line with my cubic surface, so this thing is given by a linear equation. This thing is given by a degree 3 equation. So if we look at the solution sets where both of these are 0, we should get three solutions. And so one of those solutions is going to be this point P. It's on the line and it's on S. Another is going to be this Q, but we're going to get a third point of intersection. Maybe it's somewhere here. And we're going to call that R. So this like kind of set should be P, Q, and a third point R. So to construct this map, we'll send these 2 points just to the third point of intersection. Okay. And again, this is defined for all points on my lines, L1 and L2. Okay, so what about the inverse?
And this map is supposed to be rational?
Yes, so you can see that this is going to be given by rational functions because all you're doing is like you're taking solutions to polynomial equations. Yeah. So if you write down in coordinates.
How did you pick out the one that isn't P and Q?
Well, you can write them down. So you can write down explicitly the equation of the line that intersects P and Q. You can explicitly solve for the 3 points, and then you take the coordinates of the third point.
Okay.
Yeah.
Okay.
Yeah, so it sounds kind of like I understand the point. It sounds kind of like hairy-fairy, but the point is you have explicit equations at each step, and when you write it down, you'll see that the solutions are going to be rational functions.
Is it possible that R coincides with P or Q? I mean, we don't know if it's, got to be a repeated root or not, right?
Yeah, I guess that's a good point. Yeah, that is
maybe it doesn't matter.
point. So if it coincides with P and Q, that means your line is tangent to your surface at one of these points. I guess that could happen. Yeah, I guess you could still send it to the third point though. Yeah, I think it would still be fine, right? Yeah, because that's still a point on S. Yeah. Yeah. Okay, so now for the reverse map is a little bit trickier. And it's not going to be defined everywhere. So if we take a point S on S, what we can do is we can consider these kind of 2 planes. So S is a point, and we can take one of the lines. So let's pick L2. If we write down in coordinates, we can write down a unique plane that contains this point and this line. So this is a plane. And again, we can intersect this plane with the other line. So we can intersect with L1. And now the point of, a line is linear, the plane is also linear. This should intersect in a unique point. So we'll call that, I guess, P1. And then we do the same thing with the other line. So we take the plane spanned by S and L1. We intersect with L2. And we get another point, P2. And so this is where we're going to send this S to. So this is not defined everywhere. So this is not going to be defined for any points that lie on the line. So this is not defined for S on L1 or S on L2. Okay. Does someone have a question?
Oh. I was gonna ask about if that's where the dotted lineness came from. Yeah.
Right.
Then you answered.
Yeah. Okay. Cool. So one can check. These are kind of very geometric constructions, but you can easily check that these are actually inverse to each other. Good. So these are inverse to each other. And so what have we done? We've said that we've explicitly constructed a birational map from S to P1 cross P1, which is also birational to P2. So we're done. So we kind of, right, so, and this is true for every smooth cubic surface. So this is kind of in contrast to the one-dimensional case. So one thing I want to kind of emphasize is this, this argument isn't special to surfaces. So kind of a remark. We can use this same argument in higher dimensions. So if X is a hypersurface of P2n plus 1, so if it's a cubic, so here this would, X would be 2n dimensional. So it's a cubic 2n fold. So if X is a 2n cubic fold, and X contains two disjoint linear spaces. So it contains two subspaces that are isomorphic to Pn, so half dimensional. Then you can do the same thing. Then the same construction, just with higher dimensional, like instead of lines and planes, you're going to be taking higher dimensional things, but the same thing works. So we'll get a map from Pn cross Pn to X. Okay. So whenever you have two disjoint, so maybe let me just say this in, so for instance, let's consider dimension 4. So X would be a subset of P5. So it's a 4-fold cubic. And then what this remark says is if X contains two disjoint planes, so planes here are just subspaces that are isomorphic to P2, then X is rational. Okay. And again, this works in higher dimension. So now,
can I ask?
Yeah.
Does it have to be two copies of Pn? Can it be linear subspaces just of complementary dimensions, like a P1 and a P3?
So I think it does have to be the same dimension. I'm not sure why that is though. Yeah, I'm not sure what would go wrong. No, it definitely has to be
It does have to be the same.
Yeah, it definitely does have to be the same. There's definitely, like, I don't see any reason why like a cubic fourfold that contains a plane, like cubic fourfolds contain many lines. So you would definitely be able to find one disjoint, but it wouldn't, it's not immediately obvious that it's rational. I guess there must be something to do with like this P1.
It would have to be a P1 or a P3, right? But
yeah, oh, it would have to be P3. Yeah.
Maybe, I don't know, maybe that just doesn't happen. Could also be the case.
Yeah. Yeah, maybe it doesn't happen. I'm not sure. Yeah.
Yeah. Thanks.
That's a good question. Yeah. All right, so I have 7 minutes left, so now I'm going to ramp up. Okay, so I've kind of skipped dimension. So what have we talked about so far? We've talked about dimension 1, and we've seen that. So in dimension 1, we've seen every cubic is not rational. So they're never isomorphic to P1. In dimension 2, we've seen that every cubic is rational. So kind of the reverse. I haven't really talked about dimension 3, and that's kind of because it's kind of hard. But kind of the milestone result is that every smooth cubic threefold is not rational. And in particular, dimension 3, we can't do this construction. So we're never going to get these like two disjoint from the remark. I mean, dimension 3 is odd dimensional, so we're not going to be able to do this kind of just construction. I don't want to talk anymore about dimension 3. So in dimension 4, it's an open question. So an open question. So from the remark above, some cubic fourfolds must be rational, because we can definitely find some of them. You could even write one down that contains two disjoint planes. So the expectation is that this is very rare. So the expectation is that the general cubic fourfold, so if you looked at the space of all cubic fourfolds and just picked one blindfolded, the one that you would pick will not be rational. So somehow being rational is kind of very special. On the flip side, although this is the expectation, there are no known cubic fourfolds that are irrational. So far, like kind of every cubic fourfold that has been written down, like explicitly in like equations, has been rational. So we do know of like a large number of families which actually are rational. And so kind of what's the idea? So the idea is that somehow rationality is kind of governed or kind of depends on like special surfaces that are contained in your fourfold. So for instance, if we have two disjoint planes inside of our cubic fourfold, we get that it's rational by the previous construction. And so there's a couple of other kind of cases. Maybe let me just tell you quickly. But maybe if you don't know what the words mean, that's kind of fine. So if X, your cubic fourfold, contains a quintic del pezzo, surface, you're rational. So I guess these are like rational ones. Another example is if X contains the blow up of P2 in 10 points embedded into P5 by some special linear system, you're also rational. So somehow rationality is kind of, so the conjecture, I guess, is that rationality really depends on the surfaces that you contain. Maybe I'll just end there actually, because I think my time is up.
All right, thank you, Lisa. Are there any questions?
What's the degree of this embedded book?
Okay, so I can just write down
Or
this.
does that depend on the system?
So the system is like, you take the 10 times a line minus 3 times all of the exceptionals. E10. Yeah. Don't ask me why. The proof was like disgusting and it uses this math. Yeah.
Right, I won't.
The reason I mentioned this one is I think this one is going to help me with the cubics I'm looking at right now. Somehow.
Nice.
Yeah. But it's not clear what this is supposed to mean. Yeah.
Lisa?
A question.
Oh, go.
Tim, go ahead.
No.
Is the idea of rationality of hypersurfaces in general that, I mean, it looks kind of like PN.
Yeah.
Outside a dense, outside some, nowhere dense subspace, right?
Right.
Yeah.
So it's kind of a simplest measure. Like it's a measure of how simple
Yeah.
your variety is. Yeah.
Is it like true if does it look topologically just like PN with some blow ups or what?
Yeah, exactly. So like kind of you have some like boundary divisors. So yeah, for surfaces, birational maps are just compositions of blow ups and blow downs. So if you are a rational surface, you're just isomorphic to a blow up of P2 in a certain number of points.
Awesome, yeah. Thank you.
You're topologically just governed by P2 essentially. It gets a bit more complicated in higher dimensions. You get these existence of more complicated birational maps like flops or something, but we won't talk about that.
Thank you. Tim.
Yeah, first I want to say great talk. I really enjoyed it. Second, I have a question which may be obvious and maybe isn't to someone who's more familiar with Zariski topology than I. But would it be true that every rational n-fold is or hypersurface is birational to every other of the same sort of dimension?
Yeah, so sorry. Yeah, so if you're rational, you're definitely you're birational to Pn. So you're also birational to everything else that's birational to Pn.
Right.
Yeah, you can just compose all the morphisms. Yeah.
Nice.
Yeah. So it's like we like to consider things up to birational equivalence. It's kind of a it's like an equivalence relation on the algebraic varieties. Yeah. But then the question is, if you're looking at a specific birational like class, like all the surfaces are birational to each other, sometimes you want to find like the simplest one, or like the easiest to study example. So in like this case, it would probably be just projective space. So it's kind of the simplest one.
Right.
Yeah.
And then I have another question, which is something that I think was sort of trying to be, I don't know, like, so earlier, I mean, so when we were talking about cubic, I think it was cubic surfaces. So, well, maybe it was cubic curves in P2.
Yeah.
So, I mean, we have these three coordinates.
Mm-hmm.
And in my mind, which is sort of a very naive approach, is, okay, well, if I have a cubic and three coordinates, then now I have like 10 coefficients because I have x cubed. And so when you said that linear equations can bring this down to a single coefficient, I mean, to me, that sounds like really incredible. So I don't know if there's an easy way to see this, or if we should talk about this later, or what.
Yeah, I mean, the number of coefficients is kind of like telling you how many cubic equations you have. Yeah. Yeah. Yeah, I guess, yeah, I would kind of agree. It's, yeah, maybe let's talk about this afterwards. Because
Okay.
Yeah.
Maybe I can add one comment.
Yeah.
If you think about automorphisms of P2, they're sort of the same as automorphisms of a three-dimensional vector space. And there's a 9-dimensional family of these things, like 3x3 matrices with non-zero determinant. So you can kind of, if you think of that space as acting sort of, it doesn't have too many fixed loci or something on the space of equations, then you bring a 10-dimensional space down to 1-dimensional space.
Right.
Okay.
So that's sort of a motivation for why the numbers might work that way.
Right.
I think that's good enough for me. That sounds, I'm convinced. Okay. Thanks.
Any other questions or comments?
Nice talk, Lisa.
Thank you. I'm glad people enjoyed it. I had a lot more to say about full folds, but I didn't get there. So.
Okay, I guess that's the end of today. Thanks very much, Lisa. Great talk.
Thanks for listening, everybody.
Yeah. I'll see you guys next week. Next up is going to be Unju. I guess more algebraic geometry.
Great.
Fun. Thank you.